This video is brought to you by succeedschool.com. With complete lessons and resources, assessments, learning plans and schemes of work for students, parents and teachers, for revision, for catch-up, or just to get ahead in class, visit succeedschool.com now for your free trial lessons. Succeedschool.com. Learn to succeed. Hey class, I'm Mr Thornton and I'm going to help you succeed in your GCSE and IGCSE. This lesson, Kinetic Energy. This topic was requested by MacAg2HD. If there's a topic you'd like me to cover, then just leave a comment below. Kinetic energy is just movement energy. Any object with mass which is moving has some kinetic energy, and increasing the mass and/or the velocity will increase the kinetic energy. That's why getting hit with a foam ball would hurt a lot less than getting hit by a similar sized rock moving at the same velocity. The rock would have more mass, so more kinetic energy, and your body would have to absorb that energy on impact. Remember, we can't create or destroy energy, just store it and change what type we have. So if the rock stops when it hits you, then it has no velocity, so it no longer has any kinetic energy either. And that energy must have been transferred into you. It may sound a bit ghoulish talking about people getting hit by rocks, but understanding this idea of kinetic energy and how it behaves is actually central to a lot of our ideas about preventing serious injuries in collisions, which I'll come back to shortly. The equation for kinetic energy is kinetic energy equals half times the mass times the square of the velocity. This is an equation you need to learn. The way this is represented varies from exam board to exam board. There's no single standardized way to represent it, which physicists all over the world have agreed on. So some boards write kinetic energy as Ke, while others write it as Ek with the K as a subscript. I'm going to stick with Ke because I think it's a clearer notation at GCSE, but the calculation is the same whichever notation you prefer. The important thing about this equation is that squared symbol over the velocity. The reason squaring the velocity is so important is clearer if we look at some examples. Let's pick some values which make our calculation nice and easy to follow. Let's say that in all cases the mass is going to be 6 kilograms, and let's start out with a velocity of 2 meters per second. Ke equals half mv squared. So that's half, or 0.5 when you type it into a calculator, times 6 kilograms, times the square of 2 meters per second. 2 squared equals 4. So our calculation is a half times 6 times 4, which is equal to 12. It's a type of energy, so like all energy, it's measured in joules. The symbol for that is a capital J. So a 6 kilogram mass moving at 2 meters per second has a kinetic energy of 12 joules. Hopefully that was pretty simple to follow. The one mistake I sometimes see people make is squaring the whole thing instead of just the velocity. If you're typing this into a calculator, I recommend either using some brackets or squaring the velocity first and then multiplying by 0.5 and the mass to avoid this problem. Now let's see what happens when we double the mass. Our calculation will now be Ke equals a half times 12 kilograms times 2 squared, which gives us 24 joules. Doubling the mass has doubled the kinetic energy. This is why getting hit by a heavier object hurts more. Now let's try going back to our 6 kilogram mass and doubling the velocity to 4 meters per second. Now Ke equals half times 6 times 4 meters per second squared. 4 squared is 16, so our calculation is a half times 6 times 16, giving us 48 joules. Doubling the velocity has given us 4 times the kinetic energy. We would say that the kinetic energy is proportional to the mass. That is, if we double mass, we double kinetic energy. If we triple mass, we triple kinetic energy, and so on. But the kinetic energy is also proportional to the square of the velocity. So doubling velocity gives us 4 times the kinetic energy. Tripling velocity gives us 9 times the kinetic energy, and so on. Small changes in velocity can have a really big effect on the kinetic energy. because KE is proportional to the square of V. This is why bullets are dangerous. Although their mass is just a few grams, when they're fired from a gun, they're travelling at hundreds of meters per second. So they have a large amount of kinetic energy concentrated into a very small object. Things get even more dangerous in space. There are thousands of pieces of space junk, mainly things like debris from previous missions, in orbit around our planets. I want you to imagine a 1 gram steel bolt drifting through space. To stay in a low Earth orbit, it would have to be travelling at around 27,000 kilometers per hour. That's about 17,000 miles per hour. This is the orbital velocity of the International Space Station, which does a complete orbit of the planet every hour and a half. That's 7,500 meters per second. If this 1 gram bolt meets a spacecraft coming the other way at the same velocity, then their relative velocity will be 15,000 meters per second. Let's calculate the kinetic energy of our 1 gram bolt. Remember, 1 gram is 0.001 kilograms. KE equals half times 0.001 kilograms times 15,000 meters per second squared. The square of 15,000 is 225 million. Multiplying through by half and by 0.001 kilograms gives us a kinetic energy of 112,500 joules. By comparison, a large, high-velocity bullet fired from a rifle would typically only have a kinetic energy of around 10,000 joules. This tiny 1 gram piece of space junk could hit a spacecraft with the energy of 10 high-velocity bullets. Spacecraft need to be better than bulletproof, and all because kinetic energy is proportional to the square of the velocity. This same principle is important here on the ground too. Although the standard speed limit here in the UK in a built-up area is 30 miles per hour, there are an increasing number of 20 miles per hour speed limits being introduced in town centres and outside schools to reduce the stopping distance and the kinetic energy of cars in places where collisions with pedestrians are likely. A car moving at 20 miles per hour has just 44% of the kinetic energy it would have at 30 miles per hour. Again, that tiny change in velocity has a big effect on the kinetic energy, meaning that any collision with this slower moving car is going to be significantly less dangerous for whoever or whatever that car collides with. If we come back to the car's stopping distance too, when a driver applies the brakes, the car's kinetic energy is changed by friction, mainly into heat and some sound, as the brake pads rub against the brake discs. To stop the car, all of the stored kinetic energy that car is carrying as it moves has to be changed into other types of energy, such as heat. This can even cause some types of brakes to overheat under heavy braking, causing them to stop working properly and making the driver lose control. If a car has less kinetic energy, then it's easier to remove its kinetic energy because there's less kinetic energy to remove, and so it's easier to stop the car. Because the ease of stopping the car depends upon the amount of kinetic energy, and the kinetic energy is proportional to the square of the velocity, doubling the velocity will make a car 4 times more difficult to stop because it's got 4 times the kinetic energy. If we look at the highway code here in the UK, it specifies typical stopping distances at different velocities. Let's just focus upon the braking distance and rearrange these bars into a graph. You can see that this is actually just a y equals x squared graph. Doubling the velocity from 30 miles per hour to 60 miles per hour increases the braking distance by 4 times. This is all because kinetic energy is proportional to v squared. I'll talk more about stopping distances in a future video, and I'll add a card with a link to that video up here when it's uploaded. If you want to see how to rearrange the equation for kinetic energy, then I have a video which runs through all possible rearrangements, and there'll be a link in the description, or you can click on this card instead.
Lightning round!
Kinetic energy is movement energy and can be calculated as half times mass times the square of the velocity. Ke equals half mv squared. Because the kinetic energy is proportional to the square of the velocity, tiny changes to the velocity can have a big effect, making fast-moving objects dangerous even if their mass is low. To stop an object, all of the stored kinetic energy it's carrying must be changed into other types of energy such as heat in a car's brakes. Doubling the velocity quadruples the kinetic energy, so quadruples the stopping distance of a car, and under heavy braking the brakes may overheat and fail. Most countries have speed limits on most roads to reduce the kinetic energy of cars, making them easier to stop and making them have less kinetic energy and therefore do less damage in the event of a collision. I hope that video really helped you. If it did, it'd be great if you let me know in the comments. Remember to like, subscribe and hit the bell to get a notification the next time I upload a video. If you check the description, I've got links to my revision guides, to SnapQuiz, that's my revision website and app, and to succeedschool.com. That's my website with full lesson plans, schemes of work and end of unit tests for both teachers and students. I've also got links in the description to my Twitter, my Instagram, my Patreon if you want to support the channel, and there's links to my other YouTube channels, Not School and Not School Plays. You can also click just here to subscribe to this channel, and you can click here to check out this related video. Good luck in your GCSEs and IGCSEs, and thanks very much for watching.